There I am. I might be in the Guinness Book of World Records for the longest job title, so if you want to check later. And if you were wondering, yes, it is still raining outside. I attempted to walk from the Hilton. That was a bad idea. Speaking about evaporative condensers, where we're going to focus primarily today is on the water side and the water technology that we've developed. This is an excerpt from a recent EPA report talking about the water consumption in the U.S., saying that the population has doubled in 50 years, but the thirst for water has tripled. And roughly 2/3 of the country is suffering from water shortages. A couple of photographs to illustrate the point. Here's Lake Mead in the southwest U.S. See where the lakeshore currently is. Back here is where it used to be. So we're certainly drawing down our water supplies. This is a drought map of the U.S. from several years ago, and this is a more recent image of the same drought condition. You can see in the southwest and over much of the U.S. We're suffering from shortage of water. It's not just the United States, but actually somewhat of a global crisis. As we're seeing here over the next 30 years, we're expecting many more countries to be in a similar situation where water is in short demand or short supply. So what does that mean for us as an equipment manufacturer? Well, the water consumption and water efficiency is becoming strategically important to our designs as well as your operations. So that requirement is driving some innovation in evaporative condensers to utilize water and energy more efficiently. Talk about some of the development. Where we've been for the last 40 years is either taking your evaporative condenser and running it dry as an air-cooled condenser, or perhaps using an ATC or a similar evaporative condenser with a fin coil. The problem with these two technologies is they aren't terribly efficient. You actually have a reduction in your evaporative heat transfer. So to look at this problem, or provide you with a solution to this problem, we've spent the last few years developing some water and energy saving technology. We're going to talk about two different types of evaporative condensers today. The idea being to improve the heat transfer efficiency as well as look at some supplemental heat transfer coils. The goal being here, with this technology, we can save you up to 80% of your water consumption that you might normally have with a conventional evaporative condenser. Looking at the three different product lines, the traditional evaporative condenser, bare tube coil, which we call the ATC. The next stage we call the Eco ATC A, and then the ultimate in water and energy saving technology, the ATC DC. Touch upon these two briefly. First is the Eco ATC A. It's a very similar condenser to what you're used to, with the induced draft, axial fan design, modular, fan section, coil section, and basin section. But what's new is our Ellipta fin thermal pack coil technology. This is increase your dry capacity as well as your wet capacity. So that's the part that's really unique and giving you a higher dry bulb switchover point. Now, how do we do this? We figured out how to put fins on an elliptical shaped tube. Our basic heat transfer coil is an elliptical shaped tube. Well, to get the extended surface, to get you some of that additional, well, actually a significant amount of dry operation capacity, we wind fins on the outside of the tubes. And in this orientation, we have them set vertically in our cabinet so we don't pay a horsepower penalty, and we're able to get additional heat transfer, both evaporative as well as dry. Now, switching gears, looking at the next level, the ATC DC, this one, The design premise is actually to give you half the design MBH, or heat rejection, at 60-degree dry bulb with your standard 96.3 Fahrenheit condensing temperature. So we're trying to give you almost what you can get with an air-cooled condenser, but at the evaporative cooled condensing temperatures. The ATC DC has two sets of coils. We have the wet coil, which is the Ellipta fin used in the ECO ATC-A. We've added a supplemental heat transfer coil in the leaving airstream, which we call the arid fin pack. Now, as Vice President of Marketing, I can tell you I'm also an engineer, so you'll see some kind of silly names like Ellipta fin and arid fin pack. I didn't go to school for marketing, but hopefully it makes sense. The ATC DC has 1 and 2 cell configurations, but lots of options in terms of the box sizes that you're able to select. And we're running about 100 to 900 tons of ammonia at standard ammonia conditions. Some of the design features and optional accessories, very similar to the ATC upon which it's based. We have the ZM2 nozzle. We have an 1 1/4" opening with 1 3/8" clearance between the orifice and the deflector plate. So anything you can pump, you can pass through the nozzle. The drift eliminators in the leaving airstream, highly efficient, provide you with additional water savings. For access, we have a number of options, including a service platform, both for the nozzle as well as the fan section. And here you can see the nozzles. Super low sound fan option as well. We use that in all of our induced draft products. And then water treatment, both chemical, non-chemical, some additional options, including stainless steel for corrosion resistance. Look at an application here. Developed a case study for a recreation center here locally. A 200-ton application. We're going to look at all 3 condenser technologies. In terms of the box sizes, we've got an ATC, an ECO ATC-A, and an ATC DC. You can see they're all the same size, all the same horsepower. This is important, as in some of the centrifugal fan condensers you might be familiar with. You typically are going to have a higher horsepower when you try to run dry. In terms of the heat transfer capabilities, both at 100% and 75% load, with the 3 different options, you can see that there's 100% load switchover point for the ATC is at -30, whereas the ECO ATC, you're above 0, and with the ATC DC, full load, you're above freezing. And again, that's at condensing. As your load is shed based on the ambient temperatures, you can see that even at 75% load, now you're up to 51 degrees that you could run that condenser dry. The comparison for the water consumption, put those up. And you can see we're at just almost $11,500. Those are US dollars. For the ATC, just over $10,000. That's about 10–11% reduction in water cost. And then for the ATC DC, under $7,500. So that's a 35% savings in water cost for the year. So applications where we would use this technology, certainly when we want to conserve water, as we've been talking about. Probably wouldn't use it at an oasis, but it's almost that good. Places where the water is scarce, where we have low ambient temperatures, up north here, reduced load cycles. Places where the water cost is excessive, both for procurement, disposal, and treatment. And then even installations where we see people applying this technology as a replacement. You have a condenser, you want to be able to add a little capacity to your plant. These condensers give you more capacity per footprint operating wet, and then give you also the improved dry operation.
The reason you come to these things is because anytime you put a group of ice makers together, it's a good day. It's about trading information.
But this has been a great day. It's money well worth coming here to participate at this innovation program with CIMCO. I look forward to next year and with fresh topics that interest the staff who are trying to maintain facilities. Should prove for another great year.